Thank you very much. Thank you for staying with me to the very end. All right. Well, I would like to add some final comments on sparkle Hodge atoms and final, of course, on my part. I mean, not that the story has ended in general, neither the content of their paper, but so I mean, the idea is that whenever we have this, so let's just summarize because this is some sort of math class, right? So as input, you have smooth projective. And then H is like homology. We start with this non-Archimedean field of result series. Then you build some sort of first output. You build the same model of bundle. That for practical purpose, it's really so for practical matters. We only care about this EX, that's the base, that you can think as some kind of parameter space for bundle multiplication, where have the structure. Now what's this vector field? To the X, and we're looking to this operator. And the second output came from considering now 4 points being on some open set inside of the fixed locus here by MT. We have the generalizing spaces for B are Q bar isomorphic plus. Of these classes of representations of MT projections in Q bar. Where just for the sake of completeness, I just recall that if you pick this guy, Q polarizable, these two graded of structures, this category. This group that we are referring as MT under representations. And what I want to consider is another class of examples about this story before we move on. So, because there was this question of a poll yesterday about you see this guy is this thing as parameter space, and you are only considering splitting on this guy on this fixed locus. I mean, how do you know that you are on the right place? And I said that there's some story related to derived categories also. And I would like just to mention this in 2 cases. So if you pick X here over C, we shall pick this to be this moves complete intersection of K hypersurfaces, K hypersurfaces of degree, say di greater or equal than 2, right? So the dimension of x, we know that. So complete intersection, right? In t n minus 1. The dimension is n minus 1 plus k. Then what do you know about this guy? Right? For canonical class, we can write this I beta n, and we have the following: if x is funnel, and you pick B belonging to your base space. This example is done in this atoms with symbols by myself. That's a couple of message. Then if you pick some B here, corresponding to multiplication by the ample class, that is C1, 1, then indeed you get as eigenvalues. We have as eigenvalues we have 0, and then we have R roots of unity, where R is precisely the funnel index. R funnel index. And I mean, you know that for this kind of complete intersections, we have a famous SOD, canonical. You look to curve x, then it is like 0, 1, or R minus 1, the same hierarchy. And then this guy, that's named as Kuznetsov component. So what this kind of computation should reflect is the following: the roots of unit should reflect on this atomic kind of decomposition given by Gromov-Witten theory, the fact that you have these objects, and then the guys in the Kuznetsov component should be related to the eigenspace corresponding to the 0. Now, some explicit case. So let's put the example inside of the example. If we choose R equals to 2, and then D1 equals to D2 equals to 2. So X is the complete smooth complete intersection of two quadrants. Then what's going on here? So if you look to the Hodge diamond of this guy, this is precisely this, right? And you know by Nash's hyperplane theorem that this also, I mean, I'm gonna write this just because I mean that this comes from P5, and then you have the part that is the primitive cohomology that's purely transcendental. It's purely transcendental. And in this case, what this composition is telling us in considering multiplication by the sample class is that the subspace, the generalized eigenspace for the zero, let's say lambda equals to zero, corresponds to precisely the representation given by this curve. And this in its turn, I mean, has the analogous in the SOD. That's so the Kuznetsov component here is the perch of a genus to curve. So that's what's in the picture. And then you have so the final index here is 2. These other 2 are the this is the kind of picture that happens. Now, if we do another example in the same style, so let's pick a 2. Okay. Now we pick again. Now we pick final index 3, and then d1 equals to d2 equals to 2. So it's very similar. But the Hodge diamond in this case is the following. So 1, 1, 8, 1, 1. All classes are algebraic in this case. And by the way, I mean, these 2 varieties are rational. But if you again do this same computation, computing this guy here for the spectrum, I'm going to write spectrum, but remember, in this case here, always means collection of eigenvalues. For B corresponding to the sample class, what you get is only the following: 0, and then the roots of the unit. So here, the multiplicity of 0 is 9 as multiplicity. So you see that, I mean, if you do the computation, you get only 4 eigenvalues, and then the point is that the eigenvalue corresponds to 0 is occupying precisely 9-dimensional subspacing homology. And then, I mean, what we claim is that this point is not general enough, because the point that's general enough should actually have like a 12 eigenvalues, each corresponding to 1-dimensional subspacing homology. So this homology will fully split in 1-dimensional representations. Great classes. So I mean, what's happening in this example is that this point is not general, and in general you don't have a manners to identify whether you are in a general enough point or not. Okay. And in this case, indeed, we can argue that this point here corresponds to multiplication, like the point B that's related to the ample class is general enough. We can show that there's no further splitting if you change B to another stuff. But in this case, no, we do expect that there is further splitting if you want. So it means that like some eigenspaces are coming together here because they're concentrating on the 0.
So can you really move, or is just a theoretical statement here? In practice, can you do this practically, concretely? In other words,
in this case, you can make the computation. Yes. But so one thing then, let me just mention this also because this question.
In other words, do you have to do some kind of non-commutative outside of geometry stuff, or?
I mean, in this example, actually, you can write a disabled bundle, and then you can really like choose the according the parameters using this kind of given power story for quantum multiplication. But in this case, you can make this very explicit. But looking to this kind of example, there is this question that we leave it as a question indeed on the paper. I mean, no conjecture at all. I mean, it's just a read a question. This is the following. We are picking them. We are picking always some B general inside of this feasible focus, right? So the question is, could we instead be general enough on the even part of this guy instead? I mean, not restricting to the Hodge classes. So because this guy, it sits here. So whenever I have your picture, let's say, then you have px even, because then they have this odd part also somewhere. Then you have this fixed method. And in other words, the amount of eigenvalues for the general enough in the XMT is the same for the general enough in the X. I have this kind of like technical questions. I mean, it's really motivated by your symmetry for fun varieties. There's something written there that I don't like. I don't want you to go. But we have this. I mean, and I think that this is pretty much everything I would like to talk about atoms itself. Now, what I want to do is propose a slight modification of this. Let's consider varieties with finite group actions, where the group actions are like the group are finite subgroups of automorphisms. And then we want to try to answer questions about the G-equivariant birational geometry. And so let's move on.
One question.
Yes.
Are the mirrors for this known? And is the analog expression known?
I mean, in some cases like this one, we can do the mirror and the computation, but in general here, no. I mean, we never wrote the mirror. We wrote the mirror for these guys for doing some computations, but we really don't want to use mirror symmetry at all because we really want to compute the eigenvalues without going to London Ginsburg, so we didn't go much on this direction. In one of the examples in the paper, we really like rely on the London Ginsburg, but it was a matter of debate between the authors whether we should do this or not, because how much of this is really.
Do you see this B in the Landau Ginsburg model? Sort of. You
Yeah.
see it
Yeah,
as
yeah.
what? As kind of.
I mean,
Is it part of the potential or?
no, actually, this is a good point. I mean, if you write it for this guy, then you notice that there are some eigenvalues like are missed, like some critical, and then you have to compactify and then they happen. Yeah. So I mean, one of the reasons we didn't want to go there.
But at least you can get some inspiration about what to expect then, right?
I mean,
Then you don't you hide it afterwards.
Yeah. Yeah, I mean, so you, for instance, who wanted to do the Landau? Ludmil, like,
Of course,
a lot.
Of course, no question.
I mean, when we wrote this, then you compute the critical values and you notice that some eigenvalues are missing. But where are they? And like, if you compactify the, then there was this serious debate whether we should do like that or not, whether this is proving elsewhere or not, and then we just didn't go. We computed that.
So is that, just to, like, is the answer then the B somehow supposed to tell you which compactification?
Yeah. Exactly. I mean, and this happens in even nicer example. But, I have no opinion on
That's
that,
always
okay?
Lambda gives for interesting stuff going on at the compact with the special fibers.
Yeah, I mean, I'll say something that that's not my cup of tea, but I mean, Woodville says this pretty much every day. That when you have like the London Whisper model, what it means like to do blow up is to bring singular fiber community. That's what it should be. That's all like how he thinks about certain stuff. I mean, I don't.
Bring singular fiber from the K.
Yeah,
Yeah, you peel off one by one, sort of.
You can also think of like some vibration and you're caching another vibration.
So you're like
Kind of reduce
merging
union
two
and you spit it
vibrations.
out. Yeah.
actually, I mean, it was this way that he thought about this cubic in 2005. That's the way that you do this to make it work. I mean, without relying much on your symmetry. But he thinks of like that. Bring stuff from infinity to these blow ups. Blow down to moving to infinity now. So
That should, the point of this is not to use mirror symmetry.
Yeah.
To have a proof that.
Is good to know interpretation.
yeah, for sure. I mean, I'm sure that you appear any moment now in the room. I'm sure that you look like that.
Have this discussion.
Yeah.
Be open right now.
Yeah,
Sorry, just one
sure,
more
of course.
question in this direction. So their theorem implies that the Lambda Ginsburg model of the cubic fourfold cannot rig stuff from infinity from the Lambda Ginsburg model of the.
I mean, yeah. I don't know. I don't know this London. I mean, I don't know how to interpret this. Let's go bad atoms in terms of like what goes wrong in terms of the London Whisper guy. I mean, I can say some words that I've heard, but I really don't understand. I mean, that's like the number of liberation series on singular fibers.
I think that just means the singular fiber is complicated.
So here is the guy to answer.
What's the question?
The question is
The meaning of the.
how this bad atom on the four-dimensional cubic can be read in terms of London Whisper.
The mirror side.
Anyway,
What's the meaning of it?
there are only two Lagrange cycles. One usually two algebraic cycles. So here shown to you. This guy. And that's how actually the proof started. I mean, they couldn't prove that, but only two could be seen.
On this K3 watch that one. That's
No.
yeah, looks like. I know I said to them that was more than correct. I mean, any other London Whisper model question? I think now is the time. Okay, and
How good to know you would come in the next one.
I mean, too many hours together. I know the
Yeah,
way
pretty
he walks
impressive.
actually.
That was rather impressive.
Okay, so then what we are going to move now is to do this equivalent story. So the equivalent happens. And actually, in terms of the practical theory, there's not much difference. So you consider finite group action, where G is the subgroup of automorphism of X. And then you really want to answer questions about equivalent birational geometry, meaning now suppose that you have X and X prime with G actions, and then you would like to understand whether there's a birational map between these two guys that happens to be G equivalent. That's the kind of answers that we want to answer. And in terms of a model, I'm sorry, a model of bundle, there's not much difference. You do what you expect to do. Instead of consider fixed points by MT, you know that if the group acts on the automorphism, all of them are invariants, so the action will go to this base of this Rubinus, and you can actually consider fixed by MT cross G. And I particularly like this because when you look to this kind of a model picture, there is no mention about group of birational automorphisms at all. But now you have IG. And then you can look at this. And then you can simply define like a Hodge atoms will not be any longer representations of MET. These are these types of representations of MET, but instead of MET cross G. That's so. Changing the picture. It is okay to think about, let's call this then G Hodge atoms as Ungar linear reps empty QG. So I mean, not much difference. And then we had some invariants, like the number of Hodge classes. Now we have the additional invariant. That's just the number of invariant Hodge classes, right? So, again, an invariant. These days. So for each now, that's the note. As before, we are denoting the atoms by this. Now we just put G atoms. And then the additional invariant is this guy is the number of G invariant Hodge classes in this corresponding subspace in cohomology. And using this kind of technology, we can really produce some numerically explicit birational invariants. Now the theorem. So as before, we always have X is movement projective, right? We are going to consider a ZP action on X P prime, X generically free. I'll just assume this guy also be irreducible. This is the setup, now the hypothesis. So fix C0. This shall be a curve. Of units greater or equal than 2. Okay. Then the following. Is a ZP birational invariant. Meaning, I'm going to provide some numerical quantity, some integer number that's invariant under equivariant blocks. And it will depend on this choice of curve that you fix in the beginning. So actually, you have like a family of invariants depending on choice of curves. Let's see how it goes. So this is the invariant. We shall denote the fixed point set of this guy by Z. Of course. This is three dimension. Three dimension. So then you can always decompose these like points, curves, or surface. Okay. So is minus the number of components, the number of components in CP that are isomorphic to C or to C, right? Where let me put the part of the statement. C is a curve who has Jacobian isomorphic to C. So we are keeping track of like the curves who have this property regarding their Jacobian. Components isomorphic to that, then there is other stuff. Minus 2, the number of components in XZP that are birational to C plus P1. Meaning the surface component should be birational to this guy. And finally, is the number of ZP atoms alpha such that we have like denoted by V alpha the corresponding generalized eigenspace. We ask that the induced action, induced ZP action is different. And moreover, that these guys are always representations, right? Now because the action is trivial, you can really think of them as Q bar linear representations. So the corresponding Q bar linear representation is actually the same representation coming from the cohomology of the curve that we have fixed. And because the genus is like a greater or equal than 1, there's only one atom or curve left because it's math. So it makes sense to say that this atom is actually isomorphic to the corresponding representation of this guy. So this quantity is a birational invariant. It's like a super weird quantity. I mean, how you would think about it, right?
Is the sum or just?
Yeah, here's the sum. I mean, minus this number, minus 2 this number, plus this number. This is like an integer.
Is this some kind of Euler characteristic?
Some sort of, yes. The way that this is obtained, I mean, is a bit mysterious in many ways. But the point is that we do not mysterious, and why there is more than one invariant, right? Because what we do is the following. You can see there is fixed point data here, while this component of atoms is like some global information on the G-variety. Then what you do is you do like some big group, like some huge Z model, where you take as generators the possible isomorphism classes of the curves appearing in possible fixed point sets for all varieties up to dimension 3, and the same like the surface appearing, and you keep track of these guys by looking to the representations of the normal bundles of these components. So it's like, and you also pick a generator's possible atoms coming up to dimension 3 and the representations. So it's like a huge set. Then what you do, you mod out by blow-up relations. So you keep track of all the possible blow-ups that appear. So it's like huge computation that you have to do, huge list that you have to check. Then the relations should impose, like, should correspond to the 0 in the, when you map to Z, because then when you map the relations to 0, then you get something that's invariant in the blow-up. And this is one of these maps that appear. Like, set up the relation to be mapped to 0. That's why I like counting series. It's not much. The only tricky part is that there are a lot of computations to keep track. And that's what symbols mean in this paper.
What's the meaning of this Jacobian condition?
So the point is, one thing that's important here is about this G greater or equal than 2, because when you have elliptic curves, right, you could have non-trivial actions or like trivial modes. So the invariants of atoms that we have, like the first half of this paper, cannot keep track of this. I mean, whether you can really see the curve of trivial action or not. So then we restrict the genus to be greater or in this. And this Jacobian is because it's just a choice, and you have results without Jacobian, but it's just a choice to take care of families that have the same Jacobian, like families of smooth projective arrays whose fixed point locus. And but you want to be sure that they're like birationally different. That's all. It's a choice for the matter of application. For instance, let me tell you the example. This will justify this. So an application example. You pick P to be a monic polynomial. Of degree 3k that you assume to be greater or equal to 4 with only simple roots. Then you look to this equation here, like this variety given by this equation. X1, x2, x3 equals to P of x4. All right, now choose the Z3 action on X given by you cyclically permute this guy. So this is the action, right? Now look at the fixed point set. So the fixed point set is what is given by this equation: x squared equals to py. And the choice of the degrees and no multiple roots implies that these shall correspond to curve with genus literally equivalent to. Okay. Now this is a fine variety. You take a compactification so that the action is stands to get something that's projected. You have to resolve some singularities on this compactification, but you can do this in a way that the fixed locus doesn't change. So it shall be a curve with positive genus. So this is a setup where we can extend the action, which is locally given by this, and we can apply the result. So then what I mean is the following. Because the hypothesis are smooth projective, give some affine description. So consider this guy. Then some facts. First is that this variety is rational. It's rational. Two, there exists compactification. Of X such that the Z3 action extends with no new fixed point set components. And the third one is that the corresponding invariant in this case is precisely -1. Why? Because the fixed point set we only have the curve, right? So there is no component of birational to surface. Then you only have to rule out the case whether you have an atom appearing that's like the same atom as a lit curve. But this compactification can be made so that you only have point classes. There is no transcendental story. So then you can really make this compactification in a way that this guy will be 0. So the invariant in this case is minus 1. Now, if you want to consider any Z3 action on P3, it can never live as fixed point set a curve with a positive genus, right? I mean, it's only like a possible P1 and P2s in fixed points. So this guy will be 0. I mean, neither you can have some kind of ruled fixed surface for a curve with genus such. And then these are the most like rational of all the varieties. So there's no apple coming from curves. But for any Z3 linear action, on P3, so this means that these two guys cannot be Z3 birational equivalent. This is one of the uses of this theorem. I said something yesterday, and I just to say this to conclude. I mean, I said yesterday that in general, atom theory has been like proven very useful in dimension 4, but there is this technical difficulty about understanding atoms per two-dimensional cases. But when you do this G-equivariant story, actually we have some results that holds in any dimension, and this comes from an enhancement of a G-equivariant atom theory that comes to go into the corresponding global function form coming from the G action. And that's the last thing that I have to say. And say that we are working on like some kind of Mendelev table collecting variational types coming from atoms, where we can propose classification in terms of atomic invariants. So let's see how it goes. That's final comment. So whenever you have a X with this G action here, we can go actually to the corresponding stack that comes on the quotient. So then look into this guy. Okay. In the case that if G is finite, then if instead of dealing with this guy, we look to what goes by the name of inertia stack, that I'll be following. We run over all the possible conjugacy classes of G, and then look to the fixed point set by one of the representatives in this conjugacy class, modeled out by the centralizer. Then the singular cohomology of this guy is what goes by the name of a Chen-Ruan cohomology. This is the Chen-Ruan cohomology. This is time. Now we can do quantum cohomology here. There exists quantum Chen-Ruan cohomology. And more than that, we can build the A model of bundle for this guy here, for this stack, but looking for the cohomology on the Chen-Ruan. One of the main consequences of this is the singular cohomology of this guy, right? So in particular, applying to this decomposition, there is precisely summation of the class of G. And then xg and the centralized. Now, if you pick G equals to 1, the identity, then you get what is the untwisted sector, right? So you have X in the centralizer of one that's the full group. So using this observation, what you have is an embedding. Let's see. Here, G equals to 1, then we have star X, the full group. Okay. Now, using this, we can actually write the base of the model F bundle for the original variety sitting inside of it. So you can expect to enrich the compositions of the atoms coming because of the quantum multiplication here with the data that comes from this decomposition. And that's what we can do. So let me just say some final words. But all this construction here can also be made compatible with non-portate, the properties of non-Lewis value. So you can do better. You can really put this guy here. That's the base of the F bundle that we use to compute the splitting of G-equivariant atoms. So you can put this guy here. The consequence is that this cohomology, G cross MT, quantum multiplication, can be then this implies that there is the action, an action of this algebra here on the cohomology of the fixed points. Oops. Or in other words, said differently. When you look to the cohomology of each fixed point set or a choice of
Is there
representative.
the sum there or?
No, this is on. Sorry.
No,
Action of this on here.
for each G?
For each G, for each,
Oh, for
yeah,
each
for each conjugate class, actually. Yes. For each conjugate class. We can decompose the cohomology of this guy by some refinements of you run over all the possible G-equivariant atoms. And then these guys, or they shall be what? These are just the result of this process of CG models. In the following sense, if G equals to 1, then you have the usual atomic decomposition. Usual. So what you can do actually is to let atoms and conjugate classes. And then you pick like the conjugate class of the unit element. Then you just have like H of 1, then H of 2, and so on. Then you pick another element, have another refinement. And do vary over all the possible conjugate classes. So out of each G variety, the expectation is that we can really build this kind of table with the data coming from fixed point set. That's only possible because of this embedding. And this works some kind of like a electronic distribution of the atoms, right? So we have like alpha one, then I have like the first level in the electronic distribution, and this kind of stuff. But you could do even better. And why stop, right? You do this, but you could consider all the possible germs over your stacks, like concentral extensions, and then build new kind of this new like base of the bundles, and hence you would get a different number on your tables. So that will be like further set of numbers, and then you can have this list. Now you give two varieties. Each variety will have its own list. You start comparing the terms. If one of these are different, then you know that they cannot reach equivalent relation. And that's our proposal. Working on it. And this is it. I think we're going to